The last 4 sections of this course are dealing with what's called statistical inference. And statistical inference is a way of thinking about like the final number of a musical that brings together the entire musical, or that last chase scene in a movie that the entire movie has been building towards. We are coming together with everything that we have done in this course. Collecting data, analyzing data, all of it is coming together in the form of statistical inference. Because at the end of the day, this is really where the power of statistics comes from, where we can draw conclusions about a population on the basis of data about a sample. How powerful is it that you can go and take a sample of your population and get some data about it, whether it's an experiment or an observational study, and have an idea what's going on in the entire population. So this concept is huge. It combines everything that we've done in this course. And with that said, a lot of students do find this section very difficult because it does involve a little bit of everything. But my recommendation here is to focus on the definitions that we come up with, how they're being applied, and more importantly, how we use the formulas and the concepts from this course to answer questions. Some of the questions that you might want to answer are things like, what % of women have a college degree? And we would be interested in the whole population. Or, what is the mean survival time for patients with this type of cancer? Perhaps you've experienced some sort of diagnosis, either you or someone close to you, and you would want to know these kinds of things about the whole population. So we have to look at this from a big idea, where the numbers that we're describing a population are unknown most of the time. Most of the time that these are going to be unknown values, and we call them parameters. If you could find the data from every individual in the population, then these would not be unknown, but most of the time, we don't know these descriptors of the population. So I'm going to put this in parentheses. They're usually unknown parameters. So if we wanted to estimate a population parameter, because we don't usually know these, then what we would do is choose a sample from the population and use a statistic, maybe the mean or the standard deviation or the sample proportion. Use some statistic calculated from the sample. That's pretty easy to do. We've done that already in this course. And that is going to provide us with the estimate. Now, this estimate will be perfect, and we'll be looking in these chapters at how we can give a range of values that provide a useful estimate. So let's look at example 1. We have a study done on soda consumption. So the Gallup poll in 2015 looked at 1,009 adults in one of the 50 states or DC, and of those, 616 indicated that they actively tried to avoid drinking regular soda or pop. So we could use this information to try to understand the entire population proportion who is also avoiding regular soda or pop. So what's the parameter here? We're always trying to describe a population. So you better always start with population when you're describing the parameter. So it's the population, and here we want the proportion of U.S. adults. We want to be specific, avoiding regular soda. Now the sample statistic here is going to be our sample proportion, and we can calculate that as 616 divided by 1,009. And if we do that, we calculate 616 divided by 1,009 and multiply that by 100, it's 0.61, or about 61%. So we can use that as an estimate. From the sample, we can estimate that about 61% of adult Americans actively try to avoid regular soda. What we're going to do here is we're going to refine this word about. Okay, you should be okay with the concept that 61% is probably not the exact value for the entire population of the United States. But is it pretty close? And statistics tells us that yes, it is pretty close, and we want to figure out how close. We want to make that about more precise. So we're going to do this by calculating what's called a 95% confidence interval. And it follows some formulas. You'll probably prefer to do it in Crunchit, so I'm going to show you how to do this in Crunchit. I'm not going to actually use any of the formulas for the calculations, but we will provide them here. So what is this 95% confidence interval? It's this interval calculated from our sample data by a process that's guaranteed to capture the true proportion, in this case, well, the true population parameter, in this case, the proportion, in 95% of all samples. This method, if we repeated it 100 times, about 95% of them would actually find the true population parameter. If we were to do 1,000, then 950 of them would capture the true value. So how do these things work? Well, we're trying to estimate the true proportion of individuals in a population who have some particular characteristic. So we need to describe that characteristic as being our success here. We're going to use our sample proportion from the sample to estimate the population. It's a good starting point. But we want to determine how good that estimate is by thinking about what would happen if we were to take many, many samples. Do sample values follow a predictable pattern? It turns out they do. We know that these statistics are going to vary from sample to sample, but in the long run, there is a pattern of sampling variability that's actually described by the normal curve, so we can use our normal distribution to understand how these samples behave. And so we're going to use that pattern, or we're going to let Crunchit do that, to compute a confidence interval to find the interval of likely values for our proportion. So we need to start with this idea of the sampling distribution. What is a sampling distribution? Well, it's going to provide us the distribution of values taken by the statistic and all possible values of the same size from the same population. All right, that's a lot going on here, but imagine that we had some population and we were to take a sample of, say, 10. And then we were to take another sample of 10 and another sample of 10. If each time we found the sample proportion, then we could look at how those sample proportions were behaving. Most of our proportions should be relatively close to the true population proportion, but they won't all be exactly there. We know from our normal distribution that you're going to have a mean and a standard deviation. So the sampling distribution is going to have a mean and a standard deviation as well. So how do we find it? Well, the first thing that we're going to be focusing on is taking a simple random sample. Of that simple random sample, calculate p hat, and that is going to be the sample proportion of the successes. And if you need a reminder of how we do that, it's the count in the sample of successes divided by the size of the sample. So as long as your sample is large enough, and we'll talk about what large enough is later, but as long as it's a pretty big sample, then that sampling distribution will be a normal distribution that will have a mean equal to the true population proportion. We don't even know it, but we know that this distribution will be centered around that value. And the standard deviation is going to be given by this formula, the square root of p, 1 minus p over n, and we typically call that the standard error. You don't really need to know that, but Crunchit's going to give you a number called the standard error, and that's what that is. And then here's a general fact that we need to accept. We're not going to worry about all of the theory behind this, but what we need to understand is that when the population parameter has some value p that we don't know, it doesn't matter that we don't know it, because the theory here tells us that 95% of all samples are going to catch that true value in the interval extending 2 standard errors on either side of our sample proportion. In other words, we take our p-hat, we subtract 2 of those standard errors, and we add 2 of those standard errors. If you go back to the beginning of this course, we talked about confidence intervals. Now we're actually looking at how we calculated that margin of error. So here, our confidence interval is given by this formula. And now I'm going to switch over to technology so that you can see how this works.